Steinhauer here. Welcome back. We are talking about the shape and size and history and future of the universe. To summarize the last video, we have three basic possibilities. One is, and all three of those possibilities are dependent upon the current density of the universe. If the current density is too high, if omega matter is greater than 1, then we live in a closed universe with a spherical shape, and the universe is expanding, but it will eventually reach some maximum separation between galaxies, and then it will come back and come back together in a big crunch at the end. If the universe has not enough matter, then the universe is saddle-shaped, and it will continue expanding at non-zero velocity forever. If it's right in between those two, if the density is exactly the right amount, then it will achieve basically escape velocity, and it will continue slowing down, but will only achieve velocity 0 at time equals infinity. And we also yesterday saw that when we add up all the matter that we can see, all of the normal matter and all of the dark matter, we only get to about omega m equals 0.25. So according to the matter, we must be somewhere between this blue and this purple curve. But remember, the geometries are important here too. For omega matter greater than 1, this is a spherical universe. For omega matter less than 1, this is a curved in the other direction, a saddle-shaped universe. And omega matter equals 1 is the only one where the universe is flat. And so when we measure the mass, we predict that we'll be on this saddle-shaped universe, or one of them. And yet, when we look at the geometry of the universe, it is indistinguishable from flat. So there's a serious debate, there's a serious problem here between the density that we measure of the universe and the shape that we measure of the universe. They don't agree. So how are we going to resolve this conundrum? We need some more observational evidence, and we need another piece of the puzzle. And that piece of the puzzle was brought out only in the past 20 years or so by observing supernovae in distant galaxies. So you might remember way back when we were talking about supernovae, that there was a type of supernovae called type 1a supernovae that were really important, because type 1a supernovae, remember, are the collapsing of a white dwarf that exceeded the Chandrasekhar mass limit. And that always happened at the same mass, 1.44 solar masses. And so we expect them all to have exactly the same luminosity. And so we can use them as standard candles. And we can use them, if we see them in distant enough galaxies, to chart not only what the expansion rate is now, but how the expansion rate is changing over time. And you might remember, you might see, if we can tell what the expansion rate was in the past, that will tell us which of these curves we're on, whether it can distinguish between an omega matter equals 0.27 and omega matter equals 1. If we can get back far enough, these curves will separate. And so we see these galaxies, and we see these supernovae, and these things are bright enough that we can see them in very, very distant galaxies. Here are 3 examples of 3 galaxies on the top, and here are supernovae that have gone off in these galaxies. Here's 1, here's 2, here's 3, the supernovae that have gone off in these 3 respective galaxies. Now, these supernovae, we know are type 1As because we can take a spectrum of it and distinguish between the two. And we know what their luminosity is. So just by measuring the brightnesses of these things, we get the distance to this entire galaxy. And if we know the distance to that galaxy, and we know the radial velocity of that galaxy, which is easy to measure, we can place it on that diagram. And we've done this now for dozens, if not hundreds, of these type 1A supernovae. And we can plot them on the previous plot and see which of those curves they best match. And so here is the data. All the type 1A supernovae that have gone off plotted on that graph. And so the answer is none of the above. Something else is going on. We would have so again, this is the same plot that we saw before. This is the average separation between galaxies as a function of time. And we would have expected, based on the observed matter in the universe, for these points to fall somewhere down here between the blue and the green curves. We would expect from the current shape of the universe for these points to fall all along this green curve. And where do they fall? They fall in a region of this diagram that we didn't even consider was a possibility before. That is this orange-yellow line. And that's not a universe that even can exist as we know it. Something is causing the universe's expansion to be speeding up over time. That's what these data suggest. That's really the only interpretation of these data. There is some force in the universe that is causing the universe not to slow down as it expands, as we expect, but to actually speed up over time. What is happening? How is this possible? So this is, to understand this, we have to go back to Einstein and his calculations that he was doing soon after he developed his general theory of relativity, which, remember, is the theory that describes how matter and space interact with one another, and how specifically how matter curves space. He realized fairly early on that his view of the universe and his equations of the universe didn't quite match up. And this comes about because of his worldview at the time. Again, this is 1917. This is well before Hubble discovers that the universe is expanding. And at the time, if you'd asked most scientists how old the universe is, they would have said it's infinitely old. That gets around uncomfortable questions about what happened at the beginning. If the universe is infinitely old and has basically looked the same as it has all along forever, then you don't have to answer where it came from or where it's going. It's just always been here. So when this was Einstein's worldview, the universe is infinitely old. Now he develops his theory of general relativity, which he is obviously enamored with. It's a beautiful theory. It explains all of gravity and then some. It explains the why of gravity. It's phenomenal theory. But it made an interesting prediction. When he applied his theory to the universe as a whole, he realized that the universe couldn't be static. It had to be either expanding or contracting. And this bothered him greatly, because if you have a universe that is infinitely old and infinite in extent and unchanging, then it's difficult to imagine a scenario where the universe is expanding or contracting. And so he didn't fudge the equation. He added a term, which is mathematically permissible, to his equations. And this term had the effect of being a repulsive force. Right? So he knew that if you had a universe that was static, that the mass in the universe would tend to make that universe want to collapse back in on itself. And so in order to have a universe in which the distances between the galaxies was not changing, then you had to have an opposite force to gravity that would keep the universe static and keep it from either expand. If it were tuned to exactly the right parameter, then the universe, the inward force of gravity would exactly cancel this outward force, and you could have a static universe. He called this thing the cosmological constant. Now, fast forward the script less than a decade later, and Edwin Hubble discovers that the universe is in fact expanding, and Einstein does a Homer Simpson. Dope! He could have predicted that the universe were expanding or accelerating. And he let his worldview of how the universe had to be cloud his judgment and introduce a constant to his equations that probably wasn't even necessary. In his writings later, he called the introduction of the cosmological constant to his equations the biggest blunder of his career. He had a chance to predict that the universe would be expanding, and he missed that opportunity. Well, fast forward 80 to 90 years or so, and all of a sudden, we need a force that is going to be pushing against gravity and causing the expansion rate of the universe to accelerate. So Einstein's greatest blunder, that there is a cosmological constant, may not have been a blunder after all. It might have been it seems to be necessary. There seems to be a force that is causing the universe's expansion to accelerate. Okay, so what is this force? Well, this is embarrassing, but it's the 21st century and we still don't know what it is. We've not yet been able to detect it. We don't even really have any good theories about what it is. But what do we call it? We call the thing dark energy. Why dark? Well, the same thing with dark matter. Dark because it's not interacting with light. It doesn't give off any light that we can see. And dark in the metaphoric sense because we don't know what it is. It's mysterious. And this seems to be an energy that is associated with the vacuum of space. And so there is some energy associated with the vacuum of space that is a repulsive force that's pushing outwards, whereas the matter in the universe is trying to pull everything back together. So let's do a quick recap. There's 4% of the universe that we understand. This is normal matter. There is 23% of the universe that is matter that we know must exist because we can measure it by the rotation curves of galaxies, but we don't know what it is. We call this stuff dark matter. And this dark energy must be the other 73%. Again, we know the universe must be flat. This is omega matter. This is omega baryonic matter. This is omega dark matter. This is all the matter in the universe together. These are omega matter, the mass density of the universe. The other 73% must be this dark energy force. We'll sometimes call this omega sub lambda. That's a capital letter lambda, because that's the symbol that Einstein gave the cosmological constant in his equation. It was a capital lambda. And so matter, remember Einstein's equation, E equals mc squared. Matter and energy are equivalent. You can exchange one from the other. You can't destroy energy in any form, including matter, but you can move energy from one form to the other. Now, energy is curvature, adds to the curvature in the same way normal matter and dark matter does. So this whole thing adds up to 100%, and this gives you a flat universe, right? Because the normal matter and the dark energy all contribute to the geometry of the universe being flat. But this dark energy behaves in a much different way than the dark matter and the normal matter do, because the dark energy is an expansive force. It's wanting to cause, it's an outward acceleration. It's pushing galaxies further away, whereas the normal matter is causing the universe's expansion to want to slow down. Okay, one more thing before we move on to the next topic, and that is all of the previous video where I was talking about the 3 different models of the universe, one open, one closed, and one flat, none of those considered dark energy. And so when you're looking at those 3 possibilities, specifically the recollapsing, the critical, or the coasting universe, none of these included anything about dark energy. And in fact, the true case is none of these are correct. The true universe that we live in has a substantial amount of dark energy, and that amount of dark energy is causing the universe's expansion to accelerate. And we live in a universe more like this, where we're expanding now, and we're just starting to see that expansion accelerate and get faster and faster and faster. So it is possible to live in a universe that is flat and also accelerating if you have dark energy included. If you don't have dark energy included, then you only get the 3 possibilities that we talked about in the last class. Okay, the other thing is this dark energy seems to be associated with empty space. And so the fraction, let's go back to this diagram and this chart. The fraction of the universe that was dark energy was much smaller in the past because the universe was much smaller in the past and because there was much less space in the past. And this dark and normal matter were proportionally much higher. as the universe evolves and expands, we're not adding any matter to the universe, but we are adding empty space. And adding empty space seems to be adding this dark energy. And so this dark energy term, while it started out very low, has been getting bigger and bigger and bigger over time until today. It is bigger than the normal and the dark matter put together, and it will only get bigger over time. In the next 10 billion years, this will only get bigger, and these will both get proportionally smaller as the universe expands, and this dark energy term becomes more and more important. Okay, we'll come back in the next class and talk about what conditions were like in the early universe, some observational evidence, some other observational evidence that this theory is on the right track, and we'll end with what the fate of the universe is overall. So come back then. I'll see you there.